All right, today we're just looking at questions and things outlined for exam two. Exam two is on Thursday. I saw one question already about working homework 17 number 5, so we'll at least do some of that one. It's a kind of long problem. I don't know if we'll do the whole thing or not, but we'll do some of it. So if you have particular questions, post them so that I can see. I saw a couple of questions, like email questions, but they were related to SolidWorks type of things. We're going to do some SolidWorks actually next class on Wednesday. I'll do some SolidWorks live, assuming everything goes well with that. Let's look at first, before we do that web work problem, let's look over here and let's see. Let's first look at the outline. So I did post this. This is on today's class 20, the outline for exam 2. It'll be basically the same format as exam 1, where you'll be in Canvas. There's some multiple choice questions, there's some calculations, there's some fill in the blank, that sort of thing. And it will have, I think this adds to 106 points, so there will be a couple of extra points scattered in there that you could try and get, in case one of these problems isn't working out, then you can try and get a different problem. I do have these like 6 points each, 848 total. I'm not sure those are exactly what I'll end up with, but that's the rough idea. I don't know if I'll have each problem equally weighted or not. Maybe not, but these are the types of problems that you can kind of expect. It just might be that there might be a little bit different balancing on the point numbers, but basically we go all the way back to frames, and then we work up through beam deflection. And the problem in the chat there is about beam deflection, so we'll look at that. So it's all beam related one way or another. So we'll get on to web work. This was the problem that was asked about, and it's got 5 parts. That's why I don't know if we'll do all of them or not, but we'll do some of it. Why don't we copy it and see what we can do. I did see that this was a 4 out of 5 difficulty on an exam. This one is way more than you would ever do for an individual problem on an exam. You might have pieces of this one that would count as an individual problem, but certainly this is more than a single exam problem would have. So this is not 6 points worth of exam questions. So it looks like we have a named beam, so that means we need to go find the beam details from there. Why don't we go ahead and do that? Let's see. Let's go. That's going to be in our material properties. Actually, not material properties. It's going to be in our reference material. It was an S, but I think it was an S in a metric beam, wasn't it? It was, yeah, S152. That's not a US beam. That would be gigantic. So we need to go not to this file, but to the exam reference. Did I click? There we go. So maybe, I don't know if it's in 1 or 2. Let's see if it's in 1. Material properties. We do need these. Those are the beam deflection equations. They're a little bit blurry on my copy, but WS, here we go. So we need this table. Let's make sure we get 152 in there. So the main thing we're going to need from here, this entire question is asking about deflection, slope, all of that kind of stuff. So what we need is we need the moment of inertia. This, you can kind of tell, I don't know how big of a screen you're looking at, and you can kind of tell that this is an I-beam turned in the normal orientation. So we're going to use the XX axis. I cut off the little diagram, but XX is the normally oriented beams. YY means that there's a load that applied to what we would think of as the side of the beam. So we need the XX, and we need a 152.26 So that is, where we at? 152. It's at the very bottom here. So this row, and we need the XX, so this column, which is that number right there. So we need 10.9 times 10 to the 6th millimeters to the 4th is moment of inertia. So we got that. Oh, 10.9. Whoops. Let's see. The question about, is the exam more like homework 17.1 and 2? Let's check that real quick before we get too far into this one. Let's see. 17 number 1. That one. So let's see what number 2 is. Yes. So of these, this one, if I put a beam deflection on the more fundamental easy problems, it'd be like this. If I did a medium or not hard, maybe hard, medium or hard, but somewhere in that range, it would be more like this one. And then they start getting this one. This one's also in that category. That could be not this many questions about it. One of these questions about it, but that kind of loading. Maybe even that kind of loading, but again, only one of the questions. This loading is a little bit more involved, but if this one was on the exam, it would certainly be one of these pieces, and it would be a hard problem, and it'd be worth more than 6 points. So, yeah, for an exam, more like 1, 2, or 3 are the exam style questions. Let's see. So we have I, the deflection of the beam midway between the supports. So we're going to need our beam equation charts. Let's see if we can find a good copy of that. I think I had a nice clear copy on the first day of beam deflection. Let's see. Here? No, maybe it's on the second day. Yeah, this one. These there is one on the exam references, but this one is just easier to look at. All right. So let's go back to here. We're working on part A. We want to know the deflection midway between the supports. Okay? So this one's a little bit tricky because we've got a simply supported beam, but it has two separate cantilevered sections. AB and CD are both cantilevered sections of the whole beam, which is simply supported. We have a pin and a roller. So why don't we kind of recreate this beam and load it in a way that we can actually work with, because we certainly don't have one of these beams in this chart. All right, so let's redraw it. Again, on the exams, you may not have time to redraw everything. Do put down your work so that as much as you can, so that we can have it in case we need it to verify, you transpose some numbers or something. I don't know what you might have done, but so that we can make sure that you get credit for what you're doing. So there's that. Let's see, how did this thing look? I think the distributed load goes, from the end of the beam to the roller. So kind of from here all the way over to here. And then we'll just do this. Now I'm actually going to draw this part of the beam distributed load in a different color. I'll do it blue, just to keep it separate from that other piece. I'm doing that because the cantilevered section under the blue part of the distributed load, I'm going to have to treat differently than the distributed load between the pin and roller. So I do have a simply supported beam. Let's see, in this picture it is case number 8 with a distributed load from the pin to the roller. So I do have that. And I do have this case number 9 where it's a beam that has a concentrated moment at, in this case, the roller. It's at one end. It doesn't matter that it's at the roller versus the pin. It's just at one end. So I'm going to use the combination of case 8 and 9 with this setup. So I'm going to change this, since what I'm trying to figure out is what's happening between the supports. This is okay to do, but at least this way. So I'm going to change this setup. I'm going to copy it and paste it down here somewhere. And instead of a load here, point load, I'm going to add or translate that point load into a concentrated moment that equals, I don't know the value, let's see, F times C. So 8.9 kilonewtons times 2.04 meters. I've already forgotten those numbers. 8.9. I think it was 2.04 meters, because this is 8.9 kilonewtons, that point load, and this distance is the 2.04 meters. I think that's what it said. Yes. Okay, and I'm going to do a similar thing with my blue part of the distributed load. I'm going to have to lump only the blue part like this. So for me, those numbers were W is 7.38 kilonewtons per meter. Or, well, that's right. And that distance from the end of the beam to the pin is A, 1.95 meters. So the concentrated moment here would be 7.38 kilonewton. Oh, wait. Oh, actually, no. It would be, I need a calculator. The lumped load is 7.38 kilonewtons per meter times 1.95 meters, 14.391 kilonewtons. So the moment, the concentrated moment, would be 14.391 kilonewtons times its moment arm, which is 1.95 divided by 2, 0.975. Okay? So we'd have to do the math to figure out what those values are. We'll do that in a minute. So now what I've got is I've got something that matches the cases in my chart, and it looks like this. You know, I've got a, oh wow, pin, a roller, I mean, pin. I've got a distance between those, which we'll have to look at that. I don't know. It's labeled B, but I don't know what it is. For me, it is 6.5 meters. I've got a distributed load. Which is 7.38 kilonewtons per meter. I've got a concentrated moment here, which is 8.9 times 2.04, 18.156 kilonewton meters. And I've got one over here, 14.391 times 0.975, Oh, well, hold, that's the wrong number. 14.391 times 0.975. 14.03. I did one more decimal, so 1 kilonewton meters. This, I don't have a chart, you know, one of these that has all of those on it, but I have one where there's a simply supported beam with a distributed load, which I have case 8, and then a simply supported beam with a concentrated moment on 2 different ends here, which is 2 applications of case number 9. So we have converted it over in a way that does work for what we're trying to find, because what we want to find is the deflection of the beam at the center of the span between the pin and the roller. So if I were trying to find something on the left end of the beam or on the right end of the beam, I couldn't do, you know, this wouldn't be what I need, or it wouldn't be all that I need anyway. I'd need to do some other stuff. So let's see if we can calculate that. So this is going to be 3 cases put together. We're going to take case 8, add it to case 9 for the moment on the right end, and then we'll do case 9 again, but for the moment on the left end. And we can add all of those together using superposition, and we'll get the, in this case, we're finding the deflection in the center of the span. So case 8 is the simplest one. Let's do that first. So now I've got 3 different equations here. The one in the second column is the slope. I don't need that. I want deflection. So I've got this middle equation, which is the equation of the elastic curve, which I could use and just set x equal to half of the 6.5 meters. I could do that. Or I've got this delta max, which it doesn't tell me where delta max is, but if the beam is simply supported and symmetrically loaded, then the maximum deflection is at the center of the span. So I can use that one. So I'm going to use this last equation, that little guy, and we're going to calculate the deflection at the center of the beam due to the distributed load. So let's see. Delta, we'll call it dist, equals 5 times omega is the value of the distributed load, 7.38 kilonewtons per meter, times L. L is the length of the span, so we have to make sure that we're using the L here as the L in our diagram, you know. So it says L is the distance from the pin to the roller, which is 6.5 meters raised to the 4th. And that's the numerator. The denominator is 384 times E. We haven't gotten E. So our problem statement, where's it at? We assume that it's structural steel. So we can get E from a chart. I think it's going to be 200 gigapascals, but we'll look it up because I'm not 100% sure on that. It also says to neglect self-weight. So that's important, meaning that we don't have to also include the fact that this beam has its own weight that causes it to deflect. So let's go check and make sure the structural steel number is right. Let's open up another one so I'm not, because I need the chart that we were using. Let's see, material properties. I want the metric version, structural steel, E, it is 200 gigapascals, right there. Okay, So back in our equation, E, we can put 200. Giga means 10 to the ninth. I, that was the very first thing we got. 10.9 times 10 to the 6 millimeters to the fourth. Okay. Now we have to figure out what unit systems we've got kilonewtons in here, we've got newtons, we've got millimeters, we've got meters. So we probably need everything in newtons and meters. That's probably the most safest way to keep our units straight. So I'm going to convert this over to 5 times 7,380 newtons per meter times 6.5 meters to the fourth. 384 is just a constant in the equation. 200 pascals is already newtons per meter squared, so we don't have to do anything with that. And then 10.9 times 10 to the 6, but that's millimeters to the fourth. So I'm going to convert that over to meters to the fourth. All right. Now, the tricky part of can we get all of this in our calculator without errors? We will try. I'm working on the denominator now. All right, so I got some 83, I don't know, billion number or something. Or maybe it's 8.3 billion, I don't know. Got a big number for the denominator. It's 5 times 7,380 times 6.5 raised to the fourth power divided by our denominator. I get, this will be meters, 0.07869 meters. So that's a lot, kind of. 6.5 meter span is pretty long span. And I have some relatively heavy loads on it, so we'll say that that's okay for now, but it actually seems like it's a little bit high. But we'll carry on. We might have to come back and check our math just to be sure. But that's not the whole thing. All right, so these distributed, so that is actually pushing the beam down. So the distributed load is pushing the beam down, but in the center anyway. But the two concentrated moments that we've converted over from the distributed load on the blue part and the point load, those are trying to lift the center of the beam up. So they're going to be the opposite sign of this. So let's do the, I wrote down the right end first, so let's do that one. So that one is going to be, let's get our equation from here. Nope, here. We need case 9. Now this one gives me a equation here. Same idea. I've got a slope. I've got an equation of an elastic curve. I've got the maximum deflection and its location, but I also have this little bit, which is the deflection at the center of the beam. So that's the part I want. So M is our 18.156 kilonewton meters. L is our span squared. 16 times that same denominator we had before instead of 384 times it. let's see if we can get this. We do need to do the same thing about converting our kilonewtons to newtons and our millimeters to meters so that we have all our matching units. If you were using MathCAD or something, then you could just, let it take care of the units for you. Okay. I get a deflection of 0.022 meters. Now, we do need to make sure our signs are working out here. So the delta one, since it's pushing the beam down, I'm going to give it a negative. And since this moment is twisting the beam in a way that makes the center of the beam move upwards, I'll give this one a positive one. And then we need the left end. And we can actually use the exact same equation. It's just with a different moment in it. So the moment here is 14.031. Same length and the exact same denominator. Okay. Oops. There we go. And I get a slightly smaller number because the moment is a little smaller. 0.017 meters. And then ideally, if we can add all of these together, we would get, let's see, I've got a 0.017 plus 0.022. Those are the two bending moments, or well, not bending moments, external concentrated moments that are pushing the beam up, and then minus the distributed load, 0.07869. So I end up with a total net of negative, so it does end up moving down more than it moves up, 0.0397 meters. Let's see if that's anywhere near what WebWork actually wants us to have. YBC at the midpoint, negative 0.03969. Do I put, yes, meters. So let's see. We actually got it right. So we were pretty close. They had a few more decimals out there than we did, but by that time, I guess we were close enough that it rounded to the same number. So that would be part one. That's a really long problem. Now we're talking through it, so it's taking longer than if I just sat down and solved it, but that's a really long set of things to do for one 6-point question. So either for an exam, this is way more than 6 points. It's probably like 18 points, through 6 points for each one of these little intermediate answers, or maybe it's 20 points, 6 for each of these and 2 for the total, something like that. Or it's a simpler problem. There's only one cantilevered section, or something like that, something to make it a lot simpler, to make it more in scale with the amount of time you have available to spend on that one problem. How did you get the final answer? Oh, the final answer, I guess I did skip some steps there. The final answer is equal to delta, what I called distributed, plus delta right, plus delta left. So I added that, and that. And realizing that the distributed load is negative because it's pushing the beam downwards. Okay, yeah, yeah. The negative sign on delta distributed is important. And that's a piece of these deflection problems, because this one, most of the time, all the loads are pushing the beam down, and so they're all negative, or you keep them all positive, or they're all the same sign. But this one does have this blue distributed load and this point load that are pushing part of the beam down, but the way they would, if you visualize how this beam would actually bend, it would do something like that. So it actually does more like this, because we just calculated that the center was negative, so it actually does more like this. That's the shape of how this beam is bent. Exaggerated, but something like that. So, or it could be that it's the ends, the cantilever parts are still sloping upwards, but they're kind of bending too. So I don't know. We'd have to plot the whole thing to see what it actually looks like. But you have to visualize in your mind which ones of these loads are causing the beam to bend down, and which ones are causing it to bend up. So that's just part one, part A. Let's see if we can do some of these others. Now, if you have some other questions or you're bored with this one, then put some other questions in there. Otherwise, we'll just keep doing on this one a little bit, because it does kind of cover all. Well, could you find it? Yeah, we'll do this. All right, so we had a little internet thing. Yeah, we'll do this one because it's a slope. So back to our little curvy line here of how we think it might deflect. Basically, B is the pin. So I don't know what it's going to do, but there's some line, some line. I don't know if it's angled this way or another way, because there's a lot going on here, and that's what we want to find the slope of. And then there was a question about a frame. So yeah, we could go back to a frame problem. All right, so let's see if we can do this, and then we'll move to a frame problem. All right, so I'm not really sure if the slope is this way, or it's angled some other downwards direction, like this. I don't know which one is the slope, or if it's perfectly horizontally somehow. I doubt it is, but there's a slope there. That's what we want to find. So even this load, though, even this one over here, is contributing to the slope all the way at the pin. So we can't just, because it's not at the pin, we can't ignore it. All three of these are affecting the slope here somehow. Now we have to decide, can we still use this model? Like, does this model still produce the correct amount of slope at the pin? And I think it does. Certainly the distributed load part does. The concentrated moment here, I actually don't know if that's going to create the same slope. Well, actually, so, I have to think about this one. I haven't worked this problem in a while. So this section is actually, like, we can model it like a cantilever, and cantilevers have zero slope at the fixed part of it. So I think the pink section here actually does not contribute to the slope at B. I think it's only the distributed load and the point load. So let's do that. So the distributed load, that one should be pretty straightforward. Let's go to our chart. Oh no, where is it? Here they are. So here, the distributed load, theta 1 and theta 2. So it doesn't label theta 1 and theta 2 on this particular diagram, but it's just the slope at the pin and the slope at the roller. It's saying they're equal. Sometimes they're not. So some of these theta 1 and theta 2 are not the same equation. So we have to be careful with that, because even the one that we're about to do, they're not the same equation. But here they are. So we can do WL, we can get this guy. So this will be theta at, this was point B from the distributed load. And we'll make that a little larger so it's easier to see. So it says omega, which for us is 7.38 kilonewtons per meter. Times L, the span, which we have to use the span that goes along with this equation. So the span is from the pin to the roller, which is 6.5 meters, right there in green. Cubed over 24, and then that same E and I that we've been using. So I've forgotten them, but let's see. 200 gigapascals for E. And 10.9 times 10 to the 6 millimeters to the 4th for I. So that came out of the chart. We did that the very first thing. All right. We also have to decide this distributed load, that's going to create a slope that is not angled the way I drew this gray line. It's angled the other way. So if we want to call that positive or negative, I don't know. We'll call that a positive slope. Oh no, that looks more like a negative slope to me because it's running downhill. So we'll call that a negative slope. So this will actually be a negative number. Although I think the way they labeled it, hold up, because their equation doesn't have negative signs. So I think the way that they labeled it in their chart, oh yeah, they didn't label it. The way they labeled the other ones, they actually flipped theta 1 around to where it's measured from the x-axis, and they gave it a positive sign, I guess. Actually, this equation could work out negative, I guess. 2L, no, it couldn't. No. B squared, L squared minus B squared, yeah, that would be a positive number. So we'll just have to assign it a number based on what we think. All right, let's see what the number is, though. And remember, this will be radians. All right, so 10.9. Got to convert that over. Multiply by 200 gigapascals times 24. Our denominator is 52 something. And then 7 point, oh no, this, we're going to convert this 7380 times 6.5 to the third divided by our answer, which is our denominator. I get 0.0387, and that angle is this angle, I believe. All right. So the pink section here where I've got the blue distributed load, since that's a cantilever, the cantilever at its fixed support, which we're imagining the fixed support being the transition from pink to not pink, is zero slope. So well, let's look at the chart, make sure I'm right on how they've got our chart set up. Let's see. Yeah, so they've got the slope at the wall, or the fixed support, 0, and then the equation for the slope is actually the slope at the free end, which is not what we want. So I'm thinking the blue distributed load does not contribute to the slope at the pin. But this point load over here does. So we converted the point load to this concentrated moment. Concentrated moment over here. Now they've got a counterclockwise, and we have a clockwise one. So our signs will be opposite of what they have here. So it's basically flipping everything to where this shape is mirrored about the x-axis of what's actually happening. And theta 1, we want theta 1. So we want this ml over 6ei. But we want a negative, or we want it to be the other sign. So this will be the theta from what I called the right-hand side. Same, oh no, different moment. The moment is 18.156 kilonewton meters. Same L, 6.5 meters. We don't have to do any exponent there. And similar denominator, but it's 6 times 200. Oh, you know what? I've been writing 200 times 10 to the 9th gigapascals. That's not right. It's 200 times 10 to the 9th pascals. I just saw that. How many times have I done that? Oh, just those 2 times. So the other times I wrote it correctly. 10 to the 9th pascals. But on that one I had written 10 to the 9th gigapascals. That would be a lot of pascals. Okay. So let's see if we can calculate this number. So I get a denominator 13 something. And then 18,156 times 6.5 divided by our denominator. Get a really tiny number. 0.00922, not meters, radians. And this angle would be, let's see, how would if that's, I guess it's like that. So they're the opposite sign. I don't know how they're going to, I assume in web work they just want a positive number, like a magnitude. We'll look and see what the instructions say, but theta at B will equal what I called theta at B. I guess this is theta at B from the right-hand side. And then plus theta at B from the right-hand, you know, the point load on the right end. Recognizing that one of those is negative. I'll give the theta from the point load as a negative. So, let's see. 0387 minus 00922, 0.02948 radians. And that would end up with that. So when I drew it here, I overestimated what the point load was doing. So it really has the other direction slope. Let's see. Well, let's see if I've got the right number in here, I guess. Downward deflections with negative values. So is this a downward deflection? I think this is probably a upward deflection. I don't know. I don't know what you would consider downward deflection. Oh, well, but that's not... Oh, wait, here we go. It's positive slopes with... Oh, well. So I'm going to say that this is a negative slope. So we'll give it a negative value. Negative 0.02948. I guess radian, RAD is the unit. I don't know. No. Oh, radians is... Oh, I got that different number anyway. 0157. So there's a different number here, and it doesn't want radians. Oh, does it want it in degrees? No, it's not a degree issue. I wonder which one of these might be not giving us the right thing. Pretty sure I did the cube there. Not 100% sure, but I'm pretty sure I did. We have E and I correct because we got the other part correct. It wouldn't matter on the which one we're calling positive and negative because you don't combine either of these together and get what did they have? Where is it at? 0.0157. I am putting it in the right spot. Slope of the beam at B, yes. Okay. So let me check my math on these and see if I just entered something wrong. All right, I got the same number for the distributed load. Let's check and well, let's make sure that I'm thinking of this one correctly. Yeah, that number's right. I think I did everything in newtons, but maybe I think I would have gotten a really wrong number if I didn't do that. But I am checking to make sure I didn't do some weird thing. Let's see, 10. It looks like the distributed load is right, but maybe I'm not getting the one from the point. Yeah, the point load correct. So let me see. ML over 6EI. Okay. I got the same number again. I did them in newtons. I wanted to do them in newtons. And meters. I wanted to do newtons and meters for everything. I don't think the pink section here, it shouldn't change the slope at B. So it shouldn't change that. Not at B. Point B is the pin, right? Yes, okay. Like that would be really bad if I was not even doing the right problem. Let's see. I don't really want to get MathCAD out and, see. Let me make sure I copied the ML over 6EI from the right thing. Maybe I've got the wrong one. I got that from here. That is the concentrated moment. And we do want the moment at the other end, which is theta 1, ML over 6EI. So that part seems okay. I don't know why. Well, now that I'm looking at it, so a concentrated moment. So a concentrated moment will create a slope theta 2 at that pin. I guess it's because it's not a real fixed support. So I wonder if I just need to include the fact that I was trying to not include this, but I guess when we convert it over to this, it does create a slope at that point because it's not a real fixed support. We're just kind of for this other problem with the deflection, we did treat it that way. So I think we need to add in this guy, a ML over 6EI. No, it's not that. It would be the slope that's associated with the end the moment is applied to, which is ML over 3EI. I think we need to add that in. I originally did not think we needed to do that, but that was because I was treating it as if it were a fixed support, which it's not. It's a pin, so it can slope around the pin. So I was saying earlier, I said that the cantilevered sections, they have zero slope at the wall or the fixed support. The only problem with that is this isn't a fixed support. It is a pin, and so it is allowed to spin around there or rotate, create a slope. So I think what we're missing is theta B from that left hand, which is the blue distributed load. There's a trick. We have to use the other theta 2. And we picked theta 2 because theta 2 in our diagram here is the one that's, let me copy this. Let me copy both of those. So theta 1 and theta 2 are not the left hand and the right hand side. Theta 2 is, it's this guy, and it's the one associated with the end that has the moment applied to it. Not the fact that it's a roller or on the right hand side or any of those things. It's the fact that it's the part where the concentrated moment is applied. So that's how we know to use theta 2 if we're talking about if we're talking about this one, then we want the slope created on the end the moment is applied. The other one, we want the slope over here, which is the opposite end, and they label that theta 1. So that's, you got to keep those straight in your mind. So let's see if we can plug this guy in. So this will equal M. So this is the 14.031. Kilonewton meters. L is still 6.5. And the denominator is almost exactly the same, except it's 3 times E times I. So this one is going to slope the same way that we said the distributed load. Well, let's see. It's going to, yeah, it's going to have that kind of direction on the slope. So we gave that a negative sign. So this one will get a negative sign also. What's the number? 10. Let's see. We got to convert our I over. We have to multiply by 200 gigapascals times 3. So I get a 65 number in the denominator. And then 14.031 times 6.5 divided by our answer, denominator. And I get a negative 0.0139 radians again, with that kind of slope going on. So I gave it a negative to match the other one that I gave negative. And let's see if we add all of these together. So I have a, where are they all at? This one, that one, and that one. Oh yeah, and we need to erase, or we need to edit this one, because we need to move that down, right? Move that guy up there. All right. So our total is, oops, not green, plus theta B from that left hand, which is I labeled as the blue distributed load. So it'll be a plus, but it's a negative number the way I've got them situated. Although when I looked at the web work, it says that I've got my signs backwards, but that's okay. We can fix it in web work. Let's see. 0387 minus 00922 minus 0.0139, and yeah, there's our numbers, 0.01558, and that's a net effect of sloping this way. And WebWorks says that denote positive slopes with positive values, negative slopes with negative values. That's a negative slope that I just drew there. So this is a negative number that we need to put in here. And it was, and they didn't like radian, so I think we just leave it unitless. 1558. And it still didn't like it because it's 15769, so whatever. That's. What if we put round it to 6 if it likes that? No, it's got to be even closer. Well, I didn't actually round that much though. I'm not sure where. Oh, you know, I rounded the actual radian numbers. They're all rounded, so that's probably the problem. On an exam, you don't have to get off into the 10th decimal place to be okay. You're okay at 3. Can I explain why you gave negative signs to some of the angles? All right, so first of all, I gave the wrong signs according to WebWork. But why I did, it would probably help if I never drew it. All right, so let's look at each piece of this individually. So here is our little beam. Okay, and we put I've lost my pen. Oh, put it in its holder. We put a distributed load on this. And we said that, hey, that distributed load is going to make the beam do that. So something like that. Extreme version of that. Which the slope at B then is this guy. Right? And so I calculated that angle. I call that one theta dist, I think. Or theta B dist. I think is what I called it. All right. Then I said that, well, that's not the only thing that's creating a moment, or not a moment, but is creating a slope at B. So we did the same thing, but instead of thinking about the, I'm going to have to redraw it because that's got too much stuff to erase. Instead of saying that the distributed load was causing it to have a slope at B, then it had a point load on the right-hand end. Now we know that the beam is out here with a point load on it, but we don't have something that, we don't have one of these charts that has that scenario in it. So what we do have is we converted that point load off at the end of the beam into this guy. And we said that, well, that is going to make the beam, if I twist it on the beam in that way, then it's going to do something like that to the beam, which would give that kind of slope, something like that. And this one I labeled theta B right. And those two, the B dist and the B right, are clearly, you know, the not the same direction. So what I was supposed to have done according to web work, and it makes sense, is I should have given the B dis the negative number because it's a negative slope, it's pointing downwards, versus the B right having a positive slope pointing upwards. So I gave them the wrong sides when I calculated here. But when I put them in web work, I gave them the right signs. But so I actually gave them the wrong signs here. These green highlighted numbers should all be the opposite signs. But that's why I gave them different signs. And then just to just so my notes are complete here, let's do the other one. Whoops. So we've got our roller, and we've got our pin, and we knew that really the beam is out here, and there's a distributed load. I actually drew it blue in my original picture over there, but we don't have one of our cases in our chart that handles that. So we said that, well, we do have this. Well, we sort of have this. This is case 9, but it's the mirror image of case 9 in this chart. So, case 9 has the moment, when it draws the picture, it has the moment on the right-hand side, and we have the moment on the left-hand side of the beam. So it's the mirror image of that one. And we know that this, by itself, would cause the beam to do something like that, which at B would give us this kind of slope again. I named it theta B left, and since it has that kind of slope, I gave it the same sign as I gave B right. So in mine, again, I gave them both negative signs. They should have been positive because they have positive slopes. They're pointing upwards. But for whatever reason, I was thinking backwards. All right, so hopefully that explains why they have different signs and why I gave them the wrong signs, actually. All right, but I'll give you a second to catch up and see, are there any other questions about this problem? And then if not, we'll go look at a frame or something. We haven't looked at frames in quite a while. All right. I think we're probably good on this problem. The other sections, the other parts of this problem are similar iterations of the same thing. It's just we want to find the deflection at point A. That one's a little bit different. We did do a problem very similar to that one. It might have been the very first beam deflection we worked. It wasn't a distributed load. I think it was a point load on the cantilevered end of a simply supported beam. So I think we have done that one. And it kind of builds off of what we just did in part B. Again, these are well beyond an exam question in their difficulty. They're difficult, but a lot of the difficulty is so many little numbers to keep track of. And there are some even I was thinking incorrectly on this, how to deal with this part when it came to the slope. So these are a little beyond what we can ask in a few minutes for exams. That's why we put them on the homework. Let's see if we can come across a decent frame. Well, I think we've already worked that one, actually. I think we worked that one. We didn't work this one. This one is a okay one to work on. We'll do this one, and then if y'all have a particular one or something different, we'll work on it. All right. So we've got this tower crane rigidly attached at F. So down here, it's saying that I have a fixed support, is what it's saying. That's in our words of what we've been using. And when we have a fixed support, it means we have a X, a Y, and a concentrated moment reaction all at that one point F. A cable is attached at D, passes over small frictionless pulleys. We have only dealt with frictionless pulleys in the course, and we will only deal with frictionless pulleys in this course. What that means is this cable, even though it changes direction, it doesn't change tension. It's all the same tension in that cable anywhere I look at it. There's an object at C, so some kind of boulder here. It gave us a mass, so we have to be careful with that because that's not a force. So we got to convert our 1,400 kilograms times, and I don't know if it's going to be 9.81 or 9.8. I'll go with 9.81, and hopefully WebWorks is happy with that. A bunch of dimensions, and we want to find all forces acting on member A, B, C, D. And then the reactions at F, and some stress stuff, a shear stress problem. All right. Let's start with the free body diagram. So what I'm going to do, I think, is I'm basically going to, cut this thing loose. I guess I'll probably cut it closer to like right along that surface there. And draw the free body diagram of the whole thing. I'll simplify it so that we don't draw all the little individual truss pieces, though. I was drawing in green. So there's A, B, C, D, just all one piece. E, B, F, I'm just going to draw as a vertical rectangle. Something like that. And for this piece, I'm going to draw, whoops. Scrolled way off the screen for me. There's that. And that. I'm ignoring the rollers there. I'm not too interested in those. I don't know what this is, though. So I'm just going to call it T for the tension in the cable. That's all one cable there. I didn't draw the pulleys or anything, but there are, there's a little pulley there. Maybe I shouldn't draw them in red. But there's another little pulley here that the cable goes around, and then there's a pulley over here. Actually, no, there's not a pulley at that point. It's just terminated there. There is some cable here, and I do know its force. I didn't calculate it, but it is. Get my calculator on. 1,400. I'm going to go with 9.81. So times 9.81. 13,734 newtons. And then at F, I've got Fy. I've got Fx. And I've got the moment at F. And I've got a whole bunch of dimensions. So I'm not going to transfer all the dimensions, at least not right now. What I want to know is all the forces acting on member A, B, C, D. First, I'd look at it, and my normal thing is, well, I want to find all these external reactions. The only problem with that is I have 4 of them. Well, I have 3, Fx, Fy, the moment at F, But I also have the tension in the cable, which is attached to the ground, you know, so it counts as some external thing. And I don't know that. So I have 4 unknowns and only 3 equations to work with. That doesn't give me a great deal of confidence that I can solve all of those. Looking at it, I could get that fx is 0 though, so I could do that, right? It's the only one in the x direction, so it's 0. But y is countered by both t and the 13 kilonewtons. And then the moment at f, actually, yeah, I couldn't solve any of those. So I just know fx is 0. So that means when you get stuck like that, you have more unknown external things than you have equations to solve them. You have to draw some other free body diagrams. Since it is specifically asking about the forces acting on member ABCD, I'm going to draw ABCD. So let's go down here. That'll be my free body diagram for ABCD. Oh, whoa. I was not doing what I thought I was doing. That's the tension in the rope. That's the tension in the rope. That's the tension in the rope. That is my 13.734 kilonewtons. And then B is a pin. Oh, I didn't specifically mention that when you're dealing with frames and machines, it's a good idea to look for 2 force members. All of the cables, chains, ropes, those are all 2 force members, but you know, none of the truss pieces are 2 force members. I probably shouldn't even use the word truss piece because I don't want to confuse them with the truss section that we did in exam 1. So all of the, you know, mechanical pieces here are not 2 force members. So we checked. There's no 2 force members other than the cable. B, just being a regular pin, it's going to have BX and BY. I don't know which way they should be going, so I just drew them in the positive X and Y directions. I can probably sort out some angles here. So this rope is, oh, I need to see my numbers. H2 5 over W1 7. 5 over 7. Did I do those right? H2 is 5, W1 is 7. Yes. The other triangle has the same height, so same 5. And a run of W2 plus W3. 2 plus 3 is 9 plus, what, 4.4. So 13.4. I could go and find the hypotenuse of my little blue angle triangles, or you could find the actual angle if you wanted to. I usually like doing it this way. 7 squared plus, oops, 7 squared plus 5 squared, square root of that is 8.6, or square root of 74. The other one, 5 squared plus 13.4 squared. The square root of that is 14.3. Okay. The dimension from the end of the beam to B is 7, I guess these are meters. Yeah. From B to the point where the cable is holding up the rock is 9. Uh-oh. No, I did do it right. Yeah, 9. And from here to the end of the boom I think that was 4.4. Okay. I look at this. There's a whole bunch of arrows on it. But there's only 3 unknowns: t, bx, and by. So this one we can work with. I saw a question about are you going to have to know positive and negative directions? Maybe on the difference in flexural stress being positive if it's a tensile stress and negative if it's a compressive stress. Not like in the angle thing where you got to figure out if the angle is positive or negative. Basically, if the slope is pointing upwards, the tangent line, like we drew here. Where's my cursor? The slope of the tangent line, if it points upwards, then, and to the right, I guess, up and to the right, then it is positive. Down and to the right is negative. But no, you're not going to have to know this positive and negative, only in the sense of flexural stresses. We already decided on the flexural stress when the internal, not this kind, but the internal bending moment is clockwise. Those are positive numbers. Counterclockwise is negative numbers. But not like this one. So here, back to our frame. We could just pick any of these. Let's do moments about B. This is going to be a longer equation, but as long as we keep track of everything, we should be okay. I picked moments about B. That follows my general rule of do moments about the pin or a pin, because if it has 2 unknown things there and you do moments about that point, you just eliminated 2 of the unknowns and you can solve for the 3rd one. So this equation should, even though it's going to have a bunch of pieces to it, it should give us a value for t. All right. So let's start with the rock. 13.734 kilonewtons with a 9 meter moment arm minus the y component of t on the right hand side. So t, the y component would be 5 over 14.3. It has a moment arm of 13.4 meters. Bx and by aren't in this equation, plus the angled t on the left hand side. So only the y component, 5 over 8.6, gives me the y component. It has a moment arm of 7 meters minus t times 7 meters. Has the same moment arm. All of those should equal 0. So there's a lot of stuff in there, but the only unknown is t. Okay, we're closer. Let's combine all of those t values. I think T is 16.23. That must be kilonewtons. I've left some of my units off. Let's see if that's right. Oh, do I even have? Oh yeah, no, I don't. I don't have one that tells me the tension in the cable. I've got a bunch of reactions. Oh, I've got the reactions at A, B. Yeah, I don't have one that's going to be the tension in the cable. Huh. All right. So we can't check that one. I think that's right though. All right, so let's find bx and by because those we can check in our web work. So for those, I would just pick either x equation or the y equation. So for x, I have bx minus the x component of t. So that's 13.4 over 14.3 times t, plus the x component of t, which is 7 over 8.6 times t. That's it, huh? Those are the only three in the x direction. So those equal 0. We plug in our newly found value for t and see if we can calculate a number. So bx minus 16.23 times 13.4 divided by 14.3, 15.55t, plus 7 times 16.23 divided by 8.6, 13.21t. So we combine those together. Looks like they'll be negative. Move them to the other side of the equal sign, and we get bx is 2.34 kilonewtons positive, which means I chose the correct orientation for bx. 2.34 reaction at bx 2.34 right is supposed to be positive, and I got it wrong. Oh, 2, and I wrote 2.34. Why did we get it wrong? Could be anything. Could be that I wrote that 13.4 and wasn't very careful. Let me check that. No, I have that number right. I do have quite a bit of rounding, but I don't think I have that much rounding. From a 0.34 out of 2, I don't think I have that much rounding. Oh, it could be 9.8 instead of 9.81. What does that make? Let's see. $13,720. I don't know if that's that much. I have a lot of little things going on that all together could possibly, but it seems like there's a actual error. Let me make sure I didn't transpose a number wrong. Let's see. W2 is 9, 4.4 for W3. That's fine. W1, H2, 5 and 7. Those all look fine. I don't know. These seem okay to me. That one's fine. That one should be fine. That one's just times 7. Let me make sure I actually put the right numbers in. Yeah. Okay. Yeah, that seems all right. You got 1520 for the first T. Yes, you got the right number. Okay. And you have 1520 for the in 1555. So right there. Oh, I did too. Huh. I don't know how I put some number in wrong. So yeah, it's right there. So combination of rounding and somewhere in that area I typed something wrong in the calculator. And so this comes out to be basically 2 kilonewtons. By would be the same idea. You would just write the y equation, and you'd have by. Each of these t's would have a y component. You've got the 13 kilonewton, and you've got the negative t over here. So there's all of the things other than bx would be in that equation. That's a little... like the concept here is not beyond what a test question would be. There's just so many little pieces to this one that's a little beyond a test question, but that's the way we would work a frame. Let's see what else we have in here. Next problem. I don't know if we ever did this one. Let's see what else we have. Well, that's the last of the frames there anyway. This one's not tricky, but it does have this slot over here. It might be worth it to at least draw the free body diagrams. Oh, so this one does, I think we did do this one actually, or at least one like it. So this one thing you notice right off the bat, there's no 2-force member, so you look and you don't find a 2-force member, which would be a member that has 2 pins and no force applied to the body. It could have forces applied to the pins, but not to the body of that piece. This one doesn't have any of those. But then you notice that it has, instead of a pin and a roller like we normally have, it has a pin at A and a pin at E. So that tells you right away that you're going to have to treat this one a little bit differently than what we normally do, because we normally go in and use a pin and a roller, so there's 3 external reactions. But when we put 2 pins on here, there are 4 external reactions, and we only have 3 equations, x, y, and a moment equation. So this one tells you that there's something different. Usually what it's telling you is that one of those pins is connected to a 2-force member, but that's not the case in this one. This one's a little bit trickier in the sense that the unique piece to this is that slot. So it probably would be good to... let's work on this one a little bit. And if y'all are... so let's see what time we're at. We're pretty close to running out of time. Wednesday, we can also do questions. I do plan on doing SolidWorks during the live stream, you know, how we're doing the labs. But if there's more questions, I'll just do those instead of SolidWorks. But let's work on this one some. This one, I think sometimes we've used a problem very much like this one on an exam. I don't know that I put it on this exam or not, but I know it's been on some exams, or ones like this. So if we draw the free body diagram, so let's just cheat in the sake of time and pretend we're disconnecting this thing from the ground. Okay, so now we can draw a free body diagram. We have EX, we have EY. Let's put EY further down here. We don't know which way these are going, so I'm just drawing them in positive X and Y directions. We do have a lot of dimensions, so we could get AY and EY, right? Because, so we could go ahead and do that. So this is a decision point you would have to decide. Is it worth it for what the problem is asking me, on an exam anyway? Is it worth it to find AY and EY, or can I work on some piece of the problem and solve the exam problem without having to even know AY and EY? So it would depend on what's being asked. So if anything about the member BDF is the question, you don't even need to know the reactions at A and E. So you could just go straight to drawing that free body diagram. I'm going to solve these just to show you that you can, but in an exam timed situation, it might be better to look at your problem and make sure you even need to do that work. Now, if you're stuck, you've worked everything else on the exam, and you're coming back to this one, yeah, go ahead and solve for AY and EY. If you know how to do that, maybe it'll trigger the next step. So I'm going to do moments about A. And I'm going to say that, well, what that tells me is P, which for me is 680 pounds, times A plus B plus C plus E. So what is that? A plus B plus C plus, not D, plus E is 24.4 minus EY times A plus B plus C plus D. Let's see. A 5.4 plus 5.5 plus 5.5 plus 5.4, 21. Keep getting little disconnects. It's starting to thunder, so I don't know. It could go out. So then we could do summation of forces in the y direction, and that'll give us a value for AY. So you could go and get AY and EY if you thought you needed those, or maybe the problem actually needs you to solve those. But if you spent a couple of seconds looking at what the problem's asking for and figuring out, you might not even need AY and EY, depending on what's being asked. What times? Oh, yeah. So completely unrelated to frames and machines. Yeah, you can do the exam at 12 Central or 7 Central. And I'll have the Zoom link and Canvas so that you can click on that on Thursday. So what I would actually do, this problem is probably going to be asking me about member BDF. So that free body diagram, if I can get it to draw horizontal. B is over here somewhere, D is somewhere in there, and F is that point load. D is just a pin. We already decided there were no two force members. But B is the key to this one. So B is a roller in a slot. And so it doesn't say anything. Actually, it does. It says frictionless pins. B counts as a pin. It's just in a slot, not a pin that's pinned to a clevis. So how you deal with this is you treat it actually like you would treat a roller, where the reaction is perpendicular, in this case, to the slot instead of perpendicular to the surface. So it's the surface of the slot. So your reaction at B is, you don't really know which way it's going, I guess, but it's this thing. So that's the force at B. Instead of writing Bx and By, you write B, and then to figure out what angle it is, notice right here, the slot is at an angle of rise of 2, run of 1. So perpendicular to that is run of 2, rise of 1. You just invert the rise and run of your slope triangle. And that gives you a perpendicular direction. So now I've got a pretty easy setup. This is, what is that distance? From B to D is B plus C. Got too many of the same things. 11 feet, I guess. And then from D to the end over here is given as E, which is 8 feet. And I've got a really simple setup to work with. If I want to find the reaction at D, well, let's do the force at B. I would do summation of moments about D equals 0 equals 680 times 8 feet minus what I drew as B times, I only want the y component of it, so, I didn't do 1 squared plus 2 squared is, the square root of that is 2.24. So the y component is 1 over 2.24, and its moment arm is 11 feet. So let's see, 680 times 8 divided by 11 and divided by 1 over 2.24, 1107.8 pounds. Wonder if WebWork agrees. The resultant at the, let's just do this. 1105.8, 1107.8. There's not actually much, well, yeah, there's not a lot of rounding in there. I'm not sure why I didn't get the exact same number. I mean, I guess the 2.24 has some rounding. What if I put the square root of 5 in there? Wonder if it likes that better. 1 over square root of 5 times 11. Oh, wait, not that way, though. Yeah, so if I, it was the, I rounded too much on square root of 5. I should have used just the square root of 5 versus 2.24. So the actual number, 1105.84 pounds. Let's see. So then I could go forces in x, forces in y, get dx and dy, and carry on with the problem. The other thing you'll see sometimes, I don't see it in this particular problem, but sometimes one of these frames might, this is more likely for exam 3 than exam 2, but it's possible that they ask you for the resultant of a reaction at D, for instance. So if you wanted to know, or maybe it doesn't say resultant, maybe it just says reaction at D, or the forces on D. All they're telling you to do there is that equals the square root of dx squared plus dy squared. So they could, or I could, ask for what is the reaction at dx, what is the reaction at dy, or I could ask what's the reaction at D, or the force resultant at D, or the force on D. That's telling you to combine the x and y using Pythagorean theorem, just like you would any other resultant. So that's what it's telling you to do in that case. All right, we've been going, what, an hour and 40 minutes. We have technically a few minutes left if anybody wants a last question. Otherwise, we'll be back Wednesday. The plan for Wednesday is to do SolidWorks. That won't take the whole time, even if we do SolidWorks. But if there are no questions will be, why does slope flip? Oh, why does slope flip? Here. Yeah, I assume you're meaning, why did the slope flip from here to here? It's because what I'm doing is I want B, that arrow I drew at B, I want it to be perpendicular to the slot. And the slot being over here has a slope of rise of 2, run of 1. So perpendicular to that is the reaction. And that's just the definition. The definition for the reactions for slots, frictionless slots, is that the reaction is perpendicular to the slot. So it's just like a roller where the reaction is perpendicular to the surface you're rolling on. So that's why the perpendicular part, and I flipped the rise over run to make it perpendicular. So the reaction B is the reaction of the roller inside that slot. and it is perpendicular to whatever angle the slot is at. All right. So Wednesday, we will do SolidWorks and questions if you have questions. I know I've had a couple of people ask about SolidWorks Access. We'll just have to figure that out. You know, I don't exactly know. Everything over the weekend, I know a lot of stuff was down and may still be down because of the CrowdStrike or whatever that thing is, where a lot of computers in a network or an enterprise type environment had security issues, and so it could be that you can't access some of the SolidWorks on campus because of that. I'm not too concerned that you get the SolidWorks done. I think the due date was technically Saturday, but I wouldn't be at all surprised if you had access issues and may still have access issues. I haven't tried today. So if you haven't gotten it done, then just carry on, and when you do get access, then go ahead and turn it in then. I'm not super concerned with that deadline on the labs because we're having to treat the labs a little differently than in-person labs anyway. All right, I don't see any new questions. We'll be back Wednesday at noon, and then exam on Thursday. Quiz 4 is open, I believe, so you can take it. I think you can take it twice, and it takes the best effort. So if you want a little more practice, you can do that. Other practice, these optional problems in web work give you some extra practice. There is an exam practice test on Canvas on the exam 2 date. It does have, I saw one question in there where it's a integral, like you have to integrate something, and it's asking about centroids in general. Those are not on exam 2. Integration or centroids at all aren't on there, other than being in the context of a neutral axis. All right, I will see y'all Wednesday.